Okay, so I'll get started. Hi everyone. Welcome to today's lecture. So today we'll be talking about min-max optimization. This is something I've worked in myself, so I'm quite excited about this lecture. So let's get started. Just a reminder, I'm Pranay once again from last lecture. So this will be the outline of the lecture. I'll give a very brief outline of a very brief recap of what we discussed in the last lecture. Then I'll talk about some motivations and applications for studying min-max optimization. Then we'll talk about some comparison between what is the kind of problems we see when we solve minimization problems, by which I mean minimize f of x, this kind of function, versus what happens when we go to a broader and more challenging class of problems called min-max problems. So these are problems of the form minimize some with respect to some variable, maximize with respect to some other variable, this function, which is a function of two variables, x and y. And then we'll talk about a simple algorithm, which we use to solve this problem in a federated setting. And finally, I'll very briefly talk about some interesting open questions which exist in this area. So in the last lecture, we talked about multitask learning, and this was briefly the outline we discussed. First, we introduced some motivations and applications for multitask learning, where you want to learn multiple tasks simultaneously. And there were two broad paradigms we discussed. One was hard parameter sharing, where we explicitly decide which parameters of the network are shared across tasks and which are exclusive to individual tasks. Then we did it in a non-explicit way through soft parameter sharing, which was basically using the objective functions or the loss functions of our tasks to enforce some kind of shared structure between them. And a subset of this soft parameter sharing was multi-objective optimization, which we discussed has become quite relevant in the past few years. Okay, so this was a very brief recap of last lecture. Let's start with min-max optimization, which is the topic of today's lecture. So let's talk about some motivations and applications. Why would we want to study min-max optimization? So suppose we want to minimize some loss function. We are interested in some learning problem, and if we want to say achieve a smaller error or a high accuracy on some task. Suppose we have some loss function f, which and x are the parameters of the algorithm. So these are the parameters of our network, and f is our loss function. And we want to minimize this loss function. We want to find the parameters which minimize this loss function. And here z is our data, right? So z is the data we have. Suppose we want to achieve lower classification error, then z is the images we are classifying. And this data z, of course, will come from some distribution, right? But now suppose we are interested in a slightly more challenging problem in the sense that this distribution now comes from a set of distributions rather than being a fixed distribution. It can come from a set of distributions. So it can be very it can be very spread out like this distribution, or it can be very concentrated in the space of distributions like this one in yellow. So this problem, where even there is uncertainty about the distribution from which our data is coming, this is called a robust learning problem. It turns out this is a slightly more general problem than simply minimizing f of x, where our data is coming from a single distribution. So it's a slightly more general problem. Another example is, suppose we are interested in generating some artificial data. So these are all images which don't belong to actual human beings. These are artificially generated images. So in essence, we want to learn. Uh, I think someone has a question. see. Okay, thanks. Thanks. Yeah, so as I was saying, these are all artificially generated images, and we might be interested in generating similar artificial data. Uh, in essence, to do that, we want to find out what is the distribution of real data. So D is the distribution of real faces, for example. And once we have that distribution, we can sample from that distribution to generate more images of like human-like faces. So again, this is a problem which we cannot model using a simple minimization problem. So this is insufficient to solve this problem. Finally, one last example I want to talk about is that of imbalanced classification. So to look at an example, these are images of chest X-rays for different diseases. And there is a large data set of common chest diseases, which NIH, the National Institute of Health in the US, has compiled. So it has over 100,000 images. However, because different diseases have different frequency of occurrence, therefore, we get different number of chest X-rays for the different diseases. So this is sort of a distribution of chest X-rays according to the disease. So as you can see, uh, for some diseases, you get a lot more samples than you get for the other diseases, right? Now, if we want to train or learn a machine learning model, which will classify these chest X-rays into the different diseases they come from, we have to account for this imbalance in the data, right? We cannot simply try to maximize our classification accuracy or minimize the classification error. And the reason for that is, suppose there is some disease which only occurs less than 1% of the time. So it happens in less than 1% of the humans. So naturally, we'll get very few chest X-rays from this disease. If our goal is only to maximize accuracy, in that case, we can train a model which completely ignores this disease, and still we'll be able to achieve more than 99% accuracy with our model, right? But this would have very bad consequences for people who actually suffer from this disease, right? So this problem of imbalanced classification has very real world consequences. So the thing common in all these three applications, robust learning, automatic or artificial data generation, and imbalanced classification, was that we cannot model them using simple minimization problem. So I already mentioned that we cannot model them in this kind of a formulation. However, we can model them using a slightly general class of problems called min-max problems. So if we define our loss function in a clever manner, it has two sets of variables, x and y. We minimize it with respect to one set of variables and maximize it with respect to the other set of variables. So this min-max formulation is able to capture all these three problems. And as you can imagine, this is a strictly larger class of problems, because if this y is an empty set of variables, like there is nothing here, then this formulation simply reduces to our our original minimization problem, right? So this is a strictly general class of problems. And in this lecture, we want to study this problem. Okay, so let's try to understand what kind of loss functions, what kind of Fs we get when we study min-max problems. So let's look at this artificial data generation example. So there is a neural network architecture called generative adversarial networks, or GANs. This was proposed about 10 years back in a very popular paper. And it is used to artificially generate data. So the goal is we want to learn the distribution of real life samples. So we want to learn the distribution D from which real life images come from, right? And to learn this distribution, we take two neural networks and we make them compete against each other. So we have one neural network called the generator, which has parameters x, And we have another neural network called the discriminator, which has parameters y, right? So let's see what they do. This generator, as the name suggests, will generate some samples. So it takes as input some boring randomness. For example, these can be simply coming from, say, a normal distribution with mean zero and some covariance matrix, which is identity. So this is a very benign boring randomness. It takes as input as these boring randomness. And then it tries to generate some artificial data. For example, some artificial facial images, right? On the other hand, the discriminator, as the name suggests, is supposed to discriminate between two things. And what are the two things that discriminates between? So it takes two sets of inputs. The first set is the artificial data generated by the generator, and the second set of uh, inputs is some real data. So it takes as input the artificial data generated by the generator and the real data, which comes from some real life distribution. For example, these are like cartoon images, while these are real world images of humans. And the discriminator is want to discriminate which of the images it's seeing are coming from the artificial data and which of these are coming from real data. So, yeah. So it's supposed to decide which images are real and which images are fake. So as you can imagine, the generator would want that whatever images it has generated should get a high score from the discriminator, meaning the discriminator should classify them as real images. If that happens, then the generator would have fooled the discriminator, right? On the other hand, the discriminator would want to identify accurately which are real images and which are artificial images. So for the images created by the generator, the discriminator would want to identify them as fake, right? So as you can imagine, there is this conflict happening between the generator and the discriminator. So just to repeat, the generator G generates real-like samples. So these are artificial samples, but the generator wants to mimic the real-life distribution as closely as possible. It takes some random input Z. The discriminator wants to distinguish between these generated samples and the real-world samples, right?
Can I ask a question?
Yeah, sure.
So, once the discriminator model says that this is real or fake, does that label get passed back to the generator model?
Yeah, it gets feedback that this last image or this last sample was classified as fake.
I see.
Yeah, yeah. Thanks for the question. Yeah, so let's look at how we can mathematically model this. So this is what our loss function looks like. Yeah, recall that discriminator has parameters y and generator has parameters x. So let's first look at this first component of the loss function. This is related to the discriminator. So when the discriminator takes as input some real samples, so if the distribution comes from the real distribution, in that case, the discriminator would want to maybe I should erase a few things. Yeah. Yeah. So if the input to the discriminator is coming from the real distribution, then the discriminator would want to assign it a high score, right? Because it wants to correctly classify it as a real sample, right? So we see maximization over the discriminator parameters of this loss value when it is over the real distribution. On the other hand, when discriminator is getting input from the generator. So the generator gets some random input. It creates some output GX. That output gets fed into the discriminator. So when the discriminator gets these fake images, it would want to classify them as fake. Therefore, you get a minus here. So this maximization along with this minus makes sure that this score is minimized. So this part of the loss function is assigned a smaller value, right? So this is what the discriminator is doing. And then The generator is trying to minimize this whole thing, right? But it doesn't have anything to do with the first part, right? There is no x in the first part of the loss function. There is x only in the second part, right? So it is trying to minimize a negative quantity, meaning that it's trying to maximize its score, right? So it's trying to maximize this part. It's trying to maximize its score, right? So we see this conflict between the discriminator and the generator. The generator is trying to maximize its score, while the discriminator is trying to minimize the score, the samples from the generator. So therefore, we get this standard min-max formulation. Okay, now let's look at another problem which we discussed, that of imbalanced classification. But here, let's see what happens when we go to the federated setting. Like in the previous example, we didn't talk about federated learning at all. But let's see what happens when we go to the federated setting. So suppose we have a server, we have a bunch of clients, and all of them have some local data, right? Now, suppose the clients are interested in classifying the images of pets that they have on their devices, right? So suppose we have a cats versus dogs classification, right? It's just a toy example, but this will illustrate the point nicely. So suppose we have all the devices which we have in our network. Uh, it so happens that all of them only have images of cats on their devices, right? So all the existing devices only have cat images, right? However, we want to identify which images are coming from cats and which images are coming from dogs, right? And so far, all our devices only have cat images. Now, suppose a new client or a new device joins this application, this network, and this specific client only has images of dogs, right? And now we want to identify which images are coming from cats and which images are coming from dogs. Again, as I mentioned earlier, in this case, if all we cared about was maximizing our accuracy, if that was all we cared about, then we could simply ignore whatever data this device has and classify all the images we see as coming from cats, right? Suppose we have 100 clients already and 101st client joins, we can achieve more than 99% accuracy by classifying every image coming from cats, right? But that won't solve the problem. So this was a toy example, but a similar problem has had some very real world consequences. So these are some news items from over the years, and they come from Google, they come from Amazon, and they come from Twitter, right? And in all these cases, whether it was auto tagging in photos which turned out to be racist, or it was some recruiting tool in which there was shown to be bias against women, or a similar thing happening in Twitter. In all these cases, the underlying problem was that the data set which was used to train the application had a lot of bias, it had a lot of imbalance, right? So this problem of imbalanced data sets can have very real world consequences. And in a more serious application, we already talked about this briefly, but just to reiterate the point, suppose we have a bunch of hospitals which want to collaboratively train an ML model which will classify chest x-rays based on the diseases these x-rays come from, right? And now suppose at one of these hospitals, a chest x-ray for a very rare disease shows up, right? In this case, again, if you only care about maximizing accuracy, you can completely ignore this sample or misclassify it and still retain a high accuracy, right? But as you can imagine, this will have very bad consequences. So we don't want to do this. So how do we solve this problem of imbalanced classification? So one possible solution is, in this course so far, you have seen how do we solve these kind of problems where we want to learn a model X which will minimize some average loss. So here N is the number of clients. For example, in the chest X-ray example, N might be the number of hospitals. These FIs are the losses of individual clients. So what is the accuracy of classifying chest X-rays for individual hospitals? That would be an example. And to solve this imbalanced classification problem, instead of trying to minimize this average loss, one possible solution is that we try to minimize the largest loss possible across all the clients, right? So we look at what is the loss or what is the classification accuracy at every client, right? And then we try to achieve the uh, best possible performance at the worst possible client, right? So we try to look at what is the highest possible loss across all the clients, and we want to minimize it. Or in other words, we want to achieve the best possible accuracy at the client which is worst affected. So both of these are equivalent things. It turns out this has actually been done. So Chexpert is a very large data set of chest X-rays, which was compiled by Stanford University, and it was used over the years for training more and more efficient machine learning models for chest X-ray classification. And a few years back, so they maintained a leaderboard of which approach achieves the best possible performance. And a few years back, the best performing approach was proposed in this paper. And this is basically the approach they proposed. Okay. So what have we discussed so far? We looked at a number of applications where solving simple minimization problems, which we have seen so far in the course, are not sufficient to model these slightly more complex problems. And therefore, we want to model these problems using a min-max formulation. So in this lecture, we want to understand how do we solve such problems. Because so far in the course, you have talked about minimization problems and the convergence guarantees you can get. Now we have to reinvent that entire machinery, but for the more general class of min-max problems. So what are the kind of convergence guarantees we can achieve? How much computation is necessary for solving such problems? And we'll also talk about what happens when the data is distributed across multiple clients, meaning we are in the federated setting. So rather than solving this problem, we are actually solving this problem where each client has its individual loss, and we try to solve the min-max problem over the average loss. And again, what kind of convergence guarantees we can get? What kind of communication and computation resources are required. And in one of the previous lectures, you have discussed what is the effect of partial participation in federated learning. Now we want to understand the same thing, but in a min-max setting, right? So this is our goal for today. So again, as I discussed in the last lecture, because similar to multitask learning, min-max optimization has also been studied for a long time. I think like one of the classical results, which is called the saddle point theorem. So I think that result is from 1940s. So it's been studied for a very long time. So therefore, this is not going to be an exhaustive survey of min-max optimization. Uh, yeah, these are the two references I'll be focusing on. Actually, I shouldn't say that they are survey papers. They are just research papers. And the second of these is actually work in which I was involved myself. This is a very much active research area, and there are a lot of open questions here. So one of the applications I talked about was GANs. GANs was extremely popular till a few years back, but in past 2 or 3 years, it has sort of been replaced by diffusion models. And the reason for that is that the training of GANs is very unstable. And that happens because GANs are essentially modeled as min-max problems. Because min-max problems are less understood, So GANs are also, the training of GANs is also not well understood. So if we can understand min-max optimization better, we can potentially improve the performance of GANs also. So this is very much an active area. I'll talk about one very basic algorithm, and that will pretty much be used throughout the lecture. I'll generalize it in several ways. So this algorithm is called gradient descent ascent, and you are already familiar with gradient descent. So this is a small generalization on top of that. I'll talk about how min-max problems are different from minimization problems. Now, it turns out in some cases, these two are very similar, while in other cases, they are very, very different. So it's a very interesting question in itself. Then I'll go to the federated setting. I'll first talk about local stochastic gradient descent ascent. So this will be a federated version of this algorithm. Just as in this course you have looked at local SGD, which is a federated version of SGD. Similarly, that's what we will do here. We'll look at the results, complexity results, communication requirements for different classes of functions. So I'll talk about a few classes of functions. And then I'll talk about some of the more practical variants of the algorithm. So initially, I'll talk about a very specific, very restrictive kind of algorithm, but later I'll generalize it much more. Okay, so this was building up to the motivation for min-max optimization, as well as what we'll discuss going forward. So I'll stop for maybe a minute or so and wait for any questions which you might have. Can you explain page 14 again? Okay, let me go back to page 14. Is this the one you mean? Yeah, so here what I wanted to discuss was that we have a bunch of hospitals which are like instead of devices, we have a bunch of hospitals. So you can consider each hospital as a client. So this is client one, this is client two, and so on. And we have a bunch of clients. And the application we are interested in is classifying chest X-rays, right? So every hospital has its set of chest X-ray images. Now, what the hospitals want to do is collaboratively learn a machine learning model which will help them classify chest X-rays as accurately as possible, right? This is an example of federated learning, like you have seen so many times in this course. But the twist here is that because these are chest X-rays, once in a while, a patient would appear at a hospital who has a very rare uh, chest condition, right? So this specific chest X-ray, suppose it comes from a very rare disease. In this case, now you have two tasks. The first is that you do want to classify as many chest X-rays accurately as possible, but you have another task that you don't want to misclassify X-rays for rare diseases, right? Because if you misdiagnose a patient, this can have very bad consequences. So this is especially important in this like application. So what I wanted to mention was that here, just maximizing the classification accuracy might not help because maximizing the classification accuracy, one of the possible strategies is you simply ignore this chest X-ray or you like don't care about how it is classified, right? Suppose you have like 10,000 chest X-ray images. If you misclassify one of them, your classification accuracy isn't affected much, but that patient might have very bad consequences, right? So therefore, then we move to, rather than solving a minimization problem. So solving a minimization problem is essentially trying to maximize the accuracy. But here, because we care about also not misclassifying, so we go to a more sophisticated formulation. Okay, so let's continue. So now let's see how min-max problems are similar to minimization problems and how they are different. So let's first recall a few definitions. I'm sure you have seen these in this course, but just for the sake of completeness. So suppose we are given some function g. Let's first discuss what do you mean by smoothness. So if the function is L smooth, it means, so one of the possible definitions is that given any 2 points, x1 and x2, this inequality is satisfied. And what this inequality is saying is, at any point x1, we can always upper bound the function by a quadratic, right? So you might have seen the definition of smoothness, which depends on this kind of inequality. It turns out that both these definitions are equivalent. So here I'm saying that smoothness implies that at every point, the function can be upper bounded by a quadratic function. So as you can see, this is a quadratic function. Next, let's talk about strong convexity. Strong convexity is sort of complementary to smoothness. Strong convexity implies that at every point, so at every point x1, you can lower bound the function by a quadratic. So smoothness implies you can upper bound the function by a quadratic, and strong convexity means you can also lower bound the function by a quadratic, right? If we, instead of strong convexity, we have just convexity, then it means that we have a mu strongly convex function where mu is zero, right? So if in this inequality, your mu is zero, so then this term disappears and we are left with just this much. And this is the standard definition of convexity, that you can always, like, the tangent of the function lower bounds the function at every point, right? And because we are going to talk about min-max problems, so we'll also talk about concavity, strong concavity, and so on. So that means that if some function g is strongly convex or convex, in that means or that is equivalent to the negative of this function being concave. So if the function is convex, it means the negative is concave. If the function is strongly convex, it means the negative is strongly concave, right? So concavity should not, like, once you're familiar with convexity, concavity shouldn't scare you. Okay, just one more definition. So when we are considering min-max problems, this should be F here. So when we are considering min-max problems, you would recall that when we were solving minimization problem, we were concerned with minimizers or optimum point. In the case of min-max problems, the optima is defined as, or it's called a saddle point. So if a specific point is a saddle point, it means the following. So look at the function value at the saddle point. Because you are minimizing the function with respect to x at the saddle point, keeping y the same. So if we keep y the same, y star in both these cases, then x star minimizes this function. So keeping y fixed, x star minimizes this function. On the other hand, because we are maximizing the function with respect to y, so suppose we keep x star the same, then y star is maximizing the function. So you get two sets of inequalities. So keeping y fixed at y star, the minimum value of f is achieved by x star. Similarly, keeping x fixed at x star, the maximum value of the function is achieved at y star. So, and this is true for all x and y. And so this is the classical image of a saddle point. It looks exactly like a saddle. So along one direction, let's suppose this is the x direction and this is the y direction. In that case, as you can see, along this axis here, the function is minimized, right? So along this AB curve, y is fixed. On the other hand, along this CD curve, x is fixed, and therefore the function is maximized at the saddle point. Okay. So now, once we know what is the kind of optimizer or optimum point we are looking for, let's look at a simple algorithm to achieve such a point. And this algorithm is called gradient descent ascent. And we'll also talk about its stochastic variant. But let's first start with the deterministic version, gradient descent ascent. This is the problem we want to solve. So by descent, we mean that we take a step in the direction of the negative gradient. So to update the min variable x, we take a step in the direction of the negative gradient with respect to x. So starting from some point xy, we compute the gradient with respect to x and take a step in the direction of negative gradient. And to update the y variable, the max variable, this should be plus. So to update the max variable y, we take an ascent step, meaning we compute a gradient with respect to y. So we compute a gradient with respect to y and take a step in that direction. So to update the min variable, we take a step in the direction of negative gradient with respect to x. And to update the max variable, we take a step in the direction of the gradient with respect to y. So we get descent in x and ascent in y. Here, these eta x and eta y are the step sizes or learning rates. And as I said earlier, this is a generalization of gradient descent because if we have a function which doesn't have any y, right, then this disappears and we get gradient descent, right? And if instead of gradients, we have stochastic gradients, then we get stochastic gradient descent ascent. Okay, so just to summarize, let's compare minimization and min-max problems along with their corresponding algorithms. So for minimization problems, we have gradient descent. For min-max problems, we have gradient descent ascent. And what they look like? In gradient descent, we take a step in the direction of the negative gradient. In gradient descent ascent, we take a descent step in the direction of negative gradient with respect to x. And ascent step, we take a step in the direction of gradient. We have the corresponding step sizes, eta here, eta x, eta y here. And the classes of problems you have seen so far in this course, because we have only looked at minimization problems. So we saw strongly convex functions, we saw convex functions, we saw non-convex functions, right? Now, because we have min-max problems, so we can choose one class of problems in the minimization variable and another class of problems in the maximization variable, right? So we can have convex concave. So it's convex in the x variable, concave in the y variable. We can have strongly convex, strongly concave. We can have non-convex, non-concave, and all combinations are possible, right? So we choose, like out of these three here, we choose one for the minimization variable and another for the maximization variable. So from these three, we can create 9 possible combinations, right? Okay, so we want to see how these two classes of problems, minimization and min-max, are related. Like, are there similarities? Are they different? In what cases are they different? So let's look at some classes of problems. So let's assume that we'll only focus on strong convexity or concavity. Strong concavity. Right. So for minimization problems, we are considering class of strongly convex minimization problems. So what is the result? Suppose we have a smooth, strongly convex function. We have seen the definitions of smoothness and strong convexity already. In this case, if we run gradient descent, meaning we run these kind of iterations, then if our step size eta satisfies this condition, that is smaller than 1 over the smoothness parameter, in that case, our iterates, the iterates of our algorithm will satisfy this inequality. And what this inequality is saying is that the distance of the gradient descent iterate from the minimizer. So the distance of the minimizer from the iterate, it decays exponentially. So you have something which is smaller than 1 and it is raised to the power t. So it decays exponentially and you get a multiplicative factor in terms of the initial distance. So we get a multiplicative factor in terms of the initial distance. So the distance we are from the minimizer at time step t, it decays exponentially in t, right? What happens when we go to min-max problems? So suppose we have, again, a smooth problem. Also, our function is strongly convex in x and strongly concave in y. So recall that I said if your function is strongly concave, it means the negative of that function is strongly convex. So we have strong convexity in x and we have strong concavity in y. In this case, if we run our algorithm, which we just discussed, gradient descent ascent, so meaning descent step in x, ascent step in y, and again have a similar constraint on the step size, then the result which we get is you look at how far your current iterate xt yt is from the saddle point. So x star y star is the saddle point. We look at how far we are from the saddle point. Then we get a similar exponential decay. So we get something raised to the power t, similar to what we had earlier. And we get a multiplicative factor, which depends on the initial distance. So this is the initial distance. It looks like the results are quite identical. Like in both cases, the distance we are from the solution decays exponentially in the number of iterations, right? So in this case, it seems that the result, like the two classes of problems are very similar. A simple algorithm which we proposed converges very similar to how gradient descent converges for simple minimization problem. So we get exponentially fast convergence. This is great, right? Let's generalize things a bit. Let's look at what happens in other cases. So suppose we look at convex problems. Now we don't have strong convexity. We are just looking at convex problems. Again, let's first look at minimization problems. So now we have a smooth convex function, right? And again, we run gradient descent iterations. We have some bound on the step size, and the result which we get looks like the following. So we see where we are and compare what is the difference between the function value compared to the optimal function value. So this is the minimum possible function value, and we compare it to what we have. And this distance decays as 1 over t. So as you increase the number of iterations, the distance, this difference between the function values decays as 1 over t. And in the numerator, you get some dependence on the initialization. So depending on how far you initialize from the optimum, you will get some dependence on that. But the dependence in the denominator is roughly t. Right. Now let's look at what happens for a similar problem in the min-max setting. Suppose we have a min-max problem, which is smooth, like here, and it is convex concave now. So here we had convex functions, here we have convex concave. Both of them look very similar class of problems. But now, it turns out that gradient descent ascent iterates need not converge. So you might have convex concave functions, and we'll see an example shortly, for which this simple gradient descent ascent algorithm might diverge, right? This is surprising. We just went from strong convexity to convexity, or strong convex, strong concave, to convex concave, and suddenly we lost convergence, right? So this is slightly surprising. So let's try to understand what is happening here. First, we want to understand what does it mean that GDA won't converge. Second, why is it not converging? And the third question is that is it something to do with the algorithm? Meaning, is there some drawback with GDA or gradient descent ascent that it is diverging? Or is it a problem with the class of functions itself? Like, is it some property of convex concave problems which doesn't give you good convergence? Or is it just something wrong with the algorithm GDA? So let's look at a very simple example. This is perhaps the simplest convex concave function you can imagine. So it's simply you want to minimize with respect to x, maximize with respect to y, this problem. It's a simple bilinear problem. If x and y were both single dimensional, then this would simply be xy. And the solution of this problem, or the saddle point of this problem, is at the origin, right? So let's look at what kind of iterations happen in GDA. So here, yeah, to update x, you take a gradient descent step, and because gradient with respect to x, so this gradient with respect to x is simply y. So we get this. Similarly, to update the y variable, we take a gradient ascent step, and the gradient with respect to y is simply x. So we get this, right? Let's see what is happening with these iterates. So if we compute the norm square of xt plus 1 plus the norm square of yt plus 1, using these two update expressions, it is easy to see that this we like the iterates satisfy this equality, right? What this means is that the magnitude of these norm squares is increasing over time because we have a 1 over eta square, and eta is the step size. So this quantity is increasing over time, meaning this is diverging, right? But think of it this way. We can rewrite these as xt plus 1 minus 0 plus yt plus 1 minus 0. Recall that 0 is our saddle point, right? So what we are essentially saying is that the distance from the saddle point is increasing over time. But that doesn't make sense. Like this algorithm is actually going away from the solution. And this is what we see in the figure. So this is the saddle point, this is the origin, and this is where we initialize the algorithm. And as you can see, it's spiraling out. It's going away from the algorithm as time progresses, right? So clearly GDA has a problem. Well, another interesting thing is that if we look at the average iterate, like if whatever our algorithm, the progress our algorithm has made, if we average all the iterates we have seen so far, then that average iterate does indeed converge to the saddle point, but at each time step, it is going far from the solution, right? So because it's spiraling out, on average, the average is going to the saddle point, but the iterates individually are going far and far from the saddle point. So we need an algorithm which sort of uh, brings it back in, brings the iterates back in. So it turns out there does exist an algorithm which achieves this. So the problem is with GDA rather than with the class of functions itself. Like you can indeed solve convex concave min-max problems. It's just that you cannot do it with GDA because you get this spiraling out phenomena for this very simple function. So the idea is the following. As you can see in the figure, we are spiraling out, right? So it means that at every iteration, so suppose this is our current iterate, if we are spiraling out, this means that the gradient we compute is sort of taking us outside, like whatever the trajectory, it's the gradient is pushing us away from the saddle point. So if we could somehow compute a direction which would bring us inside this trajectory, so rather than going outside, if we could somehow computer direction which takes us inside, that would solve the problem, right? And there is an algorithm called optimistic GDA which achieves exactly this phenomenon. So it sort of corrects GDA. So this should be plus and this should be minus. Sorry about the typo. So this is like if we just look at this thing in black, it's exactly the GDA algorithm. What optimistic GDA does is it corrects the direction somewhat. So what it does is you computed the gradient at the current point, and then it adds a correction. So if you are taking the gradient descent step, rather than a negative step, it adds a direction which is gradient computed at the previous point. So we are sitting at xt comma yt. We are going to xt plus 1 comma yt plus 1. Inst Instead of just adding the gradient at the current point, it also considers gradient at the previous point and it adds back in. Similarly, when updating the y variable, it subtracts this gradient at the previous point. So suppose if your gradient at the current point is pointing in this direction, and similarly your gradient at some previous iterator was pointing in this direction, if you subtract it back, then it would point in this direction, right? So if you take an addition of this and this, you would sort of go inside rather than going outside. So that is the intuition of optimistic GDA. And once you do that, you indeed get convergence to the solution. So now your iterates would indeed converge to the saddle point. It turns out there is another way. So by the way, this algorithm, like both, there is another algorithm called extra gradient method, which achieves a similar effect in a slightly different manner. And both of these algorithms have existed for over 40 years. So I think this is from 1980 and this is from 1976. So one of them was proposed by a Russian mathematician named Popov. The other was, I think, proposed by a Russian mathematician named Karpelovich. I think this was Karpelovich, and this was Popov. But their finite time convergence was proven like maybe 6 years, 5 or 6 years back. So yeah, a lot of recent work in this direction. So extra gradient method, what it does is something interesting. Uh, Starting from x and y, oops, this should be positive. Yeah. So starting from x and y, it first takes a gradient step and arrives at this intermediate point xt plus half. And then to arrive at xt plus 1, it starts from the original point. It starts from xt, but the direction is computed at the intermediate point. Right. So this is like slightly weird when you look at it for the first time, but like it has some theoretical justification. So yeah, this is the extra gradient method. And both these methods, optimistic GDA and extra gradient method, both of them ensure that for convex concave problems, you do indeed converge to the saddle point. Okay, so we have looked at strong convexity or strong convex, strong concave min-max problem, where minimization and min-max problems are very similar. Then we looked at convex concave min-max problems, where GDA doesn't converge, but you can modify it in a way that it would converge. Now let's look at an even more general class of problems. So non-convex minimization versus non-convex, non-concave min-max. Okay. So let's first look at minimization problems. I think these are also results you have seen in the course. So if we solve a minimization problems, and now we are only assuming smoothness. So as long as the functions are smooth, gradient descent iterates would satisfy this inequality. So because these are non-convex functions, now you don't get you cannot achieve optima, right? It's a hard problem, meaning you need a lot of computations. You need complexity, which is exponential in the dimension. So the best thing people hope for is achieving a stationary point where the gradient is small. And it turns out with gradient descent, you can achieve that, meaning that the gradient at a specific iteration, this gradient norm square reduces as 1 over t, where t is the number of iterations, right? So let's see what happens when we go to min-max problems. Okay, so for smooth, non-convex, non-concave, here it was just non-convex. But here the problem is even more strange. What I mean is that so far we were talking about saddle points, right? It turns out in non-convex, non-concave problems, notions like saddle point or equilibrium points, even their definitions are somewhat strange. Further, it turns out if you want to achieve locally an equilibrium point, then it's a very hard problem. By hard, I mean that there are complexity results that it would require a large number of computations to even verify that where you are is actually an equilibrium point. So now it turns out, unlike convex concave problems, so in the last class of problems, the class of problems was fine. It was just that the algorithm we came up with in the beginning didn't work. In this case, the class of problems itself is hard. So there is no algorithm you can come up with which would help you solve this problem, right? I mean, these are complexity results. So if you solve this problem, then like you break down a lot of like modern cryptography and so on. But the basic idea is that these are really hard problems, complexity wise. So for this class of problems, min-max problems are much harder than simple minimization problems, right? And therefore, it's an active research direction. There has been some progress in recent years where they have tried to solve relaxations of this problem. And yeah, this is quite interesting field of work if you're interested. So just to summarize, we started looking at min-max problems. We started with the simplest algorithm possible, which was gradient descent ascent or GDA. And we generalized it. This was a simple generalization over gradient descent. Next, we compared minimization problems with min-max problems. It turns out that if we have strong convexity versus strong convexity, strong concavity, so we have similar structure in the min variable and the max variable, then both gradient descent achieves exponential convergence for minimization problems. Similarly, gradient descent ascent achieves exponential convergence for min-max problems. So here, both minimization and min-max problems were very similar. If you go to a slightly more general class of problems where you have convexity only. Here, for minimization problems, gradient descent converges to optimum, but for min-max problems, GDA doesn't converge. So for convex concave problems, GDA doesn't converge. But we also saw that you can come up with slight modifications of GDA, such as these two algorithms, which give you convergence. And finally, with non-convexity, if with non-convexity, the picture is completely different, meaning that if you are solving a minimization problem, you can achieve convergence to a stationary point. But if we are solving min-max problems, which is non-convex in X, non-concave in Y, then even existence of local solutions is difficult to ascertain. Okay, so this was the comparison between min-max and minimization problems. Next, we'll go to solving some specifically two classes of min-max problems in a federated setting. We'll look at a simple algorithm which slightly generalizes GDA and see what kind of results we can get. So we are at the 1 hour mark, so let's take a 5-minute break and then we can continue. We'll start in about 2 minutes, but feel free to ask any questions you have so far. Okay, let's continue. So next we look at solving min-max problems in a federated setting. So let's first discuss the algorithm we'll be looking at. And as you will see, it's a simple generalization of things you have already seen. So it's a simple, like you will see it generalizes GDA, which we have discussed in this lecture, and we'll also generalize local SGD, which you have seen in previous lectures. So just to recall, we are solving a min-max problems. Our function f, it's a function of x and y. We want to minimize it with respect to x, maximize it with respect to y. But now our function, this function f is actually an average of n local functions, right? Here n is the number of clients and fi is the local loss of the ith client. Right. So let's see how the algorithm proceeds. So at the beginning of each round, the server sends its global X and Y to all the clients, right? So we are making a few implicit assumptions here. The server is sending both X and Y, and it's sending it to all the clients. So there is full participation. So it takes its global X and Y and sends it to all the clients, right? Next, the clients start doing local updates. So specifically, each client is carrying out tau local SGDS steps. What that means is that starting from the global X and Y, which the server sent, each client carries out a descent step, an ascent step. Yeah, I think I've made this mistake several times. This should be positive everywhere there is an ascent. So each client carries out tau such descent ascent steps. And to perform these steps, the clients are using stochastic gradients. So this tilde here, this tilde at the top of this nabla shows that these are all stochastic gradients. So these are stochastic gradients. So each client started with the same X and Y, which the server had sent, but then they carry out local updates using their own stochastic gradient. So these stochastic gradients are computed at local functions, FI. They don't have access to, like each client doesn't have access to the data of the other client. So these are all computed locally. Once these steps are done, then the each client, whatever its local x's and y's be, so here x1 tau, x1 tau, here 1 denotes the client and tau denotes the number of local steps. So each client sends its locally updated x's and y's back to the server, and the server simply updates them. So the server takes these xi taus. Here we are going from I equal to 1 to n, and the server simply averages them. This completes one round. So this is one round of local SGDL, and then the process repeats. Okay. So as you can imagine, there are two major costs to this algorithm. The first is communication, which are shown in red. So when the server sends its global X's and Y's to the clients, it is doing some communication. Similarly, when the clients send their locally updated X's and Y's back to the server, there is again communication happening. So in one round, there is one back and forth between the clients and the server. And then there is computation at the clients. So the heaviest computation is computing these stochastic gradients. So computation means stochastic gradients. Communication means sending X's and Y's back between clients and server. Okay. So to do some analysis, let's impose a few assumptions on our problem. So I've set this algorithm, this local SGD algorithm on the side for you to look at. If oops, there should be plus again. Yeah, but let's discuss the assumptions we'll impose. The first is that all the local functions, so all these FIs are going to be smooth. We have already discussed one definition of smoothness, that you can upper bound the function everywhere by a quadratic. Here we have an equivalent definition that the gradients at 2 points are not very far from each other if the points themselves are not very far from each other, right? So we assume that all the local functions are smooth. For the stochastic gradients, so for these stochastic gradients, which the clients are computing locally, we assume that these stochastic gradients are unbiased. So at the ith client, each stochastic gradient it computes is an unbiased estimator of its actual gradient, right? In addition, we assume that we have bounded variance. So every stochastic gradient is it has a bounded variance relative to the actual gradient. Okay. And finally, because clients are carrying out multiple local steps, so starting, even though they start from the same X and Y, but in the process of carrying out these multiple local steps, they will go far from each other, right? Therefore, we need some way to bound how far they go. So one way to do this is we impose a bounded heterogeneity assumption, which means that at every client, its local gradient is not very different from the global gradient. So this is the global function. The local gradients are not very different from the global gradient, meaning they lie within a ball of some fixed radius. So H is the heterogeneity bound. Okay, so we have imposed these three assumptions. These assumptions will stay the same for the rest of the lecture. But next, we look at two sets of problems. And these two sets will have two separate assumptions. So the first is we assume that in addition to all these assumptions, our global function f, so this, which is the average of all the local functions, it is strongly concave in y. By strongly concave in y, recall that strong concavity is the same as, so f is strongly concave is the same as minus f is strongly convex. So essentially, it means that in the maximization variable, we are imposing like strong concavity or strong convexity if you reverse it. Yeah. So it's a lot more structure in the maximization variable, because we saw that for strongly convex functions there is exponential convergence to the solution. So we are imposing a lot more structure in the maximization variable. In the minimization variable, we are not saying anything. We are just saying that the function is smooth. Okay. It turns out that this class of problems has application in the data imbalance problem. So specifically the chest X-ray classification problem can be modeled with these assumptions, exactly the assumptions which I just described to you. Okay. And it was done in this paper from a few years back. So let's look at a few consequences of this strong concavity in the max variable y. Because strong concavity is like very similar to strong convexity, so it essentially means that for every x, for every value of the minimization variable, if we maximize this function with respect to y, so we are keeping this x fixed, and we solve this maximization problem, then it has a unique maximizer. And that is obvious because strongly convex functions have a unique minimizer, so strongly concave functions have a unique maximizer. And because this has a unique solution, so if we maximize our function with respect to y and get a function which is only dependent on x because we eliminate y by maximization, then this function of x is going to be well defined. What I mean by well defined is because as soon as you fix x, this problem has a unique solution, right? So there is only one value phi of x can take for any given value of x. So it is well defined. Also, this phi function is smooth, right? And smooth, we already discussed the definition. So this function is smooth. This means that starting from a min-max problem, we reduce to a smooth minimization problem, right? So starting from a min-max problem, we reduce to a minimization problem, and this minimization problem is also smooth. So there is like, this is a good minimization problem. And you have already seen in previous lectures how we solve this minimization problem. So if we solve the maximization problem, the resulting problem is something which we have already seen. And we are going to look at a stationary point of this phi. So we are interested in a point where the gradient of phi is small. Okay, so let's look at what the existing results say. So there was a paper from 2021 which solved this problem. So here this gives us phi of x, and we are interested in gradient of phi of x smaller than epsilon. Okay, so this result from 2021, it had some computation cost, meaning this was the number of stochastic gradients every client had to compute. So number of stochastic gradients per client. And this was the number of communication rounds which had to happen. So the number of back and forths between the server and the client. Because this was the first result, it was okay, but there were a few problems. First, the result was suboptimal in epsilon. So you can do better than this. And the reason we know we can do better than this is because there was another paper, even like which appeared previous to the first one, which solved this problem, but for a single client or in the centralized setting with a single like all the data at a single location, right? And it achieved certain complexity, which is clearly better than this. So because epsilon is some small constant like 0.01 or even smaller, so this is much worse than 1 over epsilon to the 4. And it turns out this result is actually optimal. You cannot do better than this. So if you want to make sure that your gradient is smaller than epsilon, this complexity is the best you can achieve. However, the problem was that this algorithm required a very large batch size. And if you have done neural network training, then you would you would see that in a lot of applications, using a very large batch size is undesirable. It doesn't give you a very good performance in a lot of cases. So this is a very restrictive assumption. So in the subsequent paper, and I was involved in both these works, we generalized uh, this result to the federated setting where you can have multiple clients and so on. We achieved a computation complexity which is optimal in epsilon. So they had 1 over n epsilon to the 4. We get a similar dependence in epsilon. And it turns out, as I said earlier, this computation cost is optimal. Also, we did not require a large batch size. We could work with a constant batch size. We also get an n in the denominator, so which means that as we have more and more clients, every client has to do fewer computations. Because recall that this computation, this is the number of stochastic gradients per client. So the number of stochastic gradient each client has to compute. So if n increases, every client has to compute fewer and fewer stochastic gradients. In the first work, so we did two works in this line. In the first work, we achieved some communication cost. And in the second one, we were able to improve this communication cost further. And now it turns out even the communication cost is optimal. So you cannot do better than 1 over epsilon square. So for this class of problems where our local functions are smooth and the global function is strongly concave in y, this is the best computation cost and this is the best communication cost to achieve a stationary point. So we are interested in a point where this is our phi of x, and we are interested in a point where phi is almost stationary. Okay, so I think I'll skip the intuition of the proof in the interest of time. I can come back to it if we have some time at the end. So we have about half an hour, so maybe we'll have some time and then I'll come back to it. Okay, so far the algorithm which we looked at, which is precisely this, it gave us some convergence, but it had some restrictions. So let's discuss what those restrictions are, and then we'll discuss how we can lift those restrictions. So first, we assume that the server sends its global X and Y to all the clients, right? So we assume that there is full participation. In every round, all the clients are available. So the server would send its X and Y to all the clients. All the clients would perform local update steps, and then all the clients would send back their local models back to the server, right? So there is full participation in all the rounds. And as you have seen in the partial participation lecture, this is a very strong assumption. Usually, the number of clients in federated learning applications are like somewhere from a few hundred to a few million, right? So you cannot expect all the clients to be present all the time, right? So therefore, this is a strong assumption. And we were able to it turns out that we are able to generalize this to the partial participation setting. So we allow that in every round, only some of the clients participate. So instead of n clients, we assume that p of them would participate in every round. So we allow partial participation. And let's see what is the effect of this partial participation on the overall performance. So this is some experiment on like robust neural network training. This is an application of min-max optimization. We did some experiments on CFAR10 dataset. The total number of clients was 15. And we ran the algorithm for 5, 10, and 15 clients, right? Also, you see there are two sets of lines for every color. So the dashed lines show that there is small data heterogeneity across clients, while the solid lines show that there is large data heterogeneity across clients. So as you can see, when we go from 15, which is full participation, so these blue curves, to 5 clients, if you have a large amount of heterogeneity in the system, the performance decays significantly. So there is like, even in terms of eventual performance, there is a drop of about 15%. And also the amount of resources you need to spend. So the performance you get is achieved after 350 rounds, while with full participation, you achieve a similar performance in, like, let's say 150 rounds. So you have to do a lot more computations, and you are also getting worse performance. So it turns out partial participation is actually a very significant source of error. Uh, I think you must have seen this algorithm FedWarp in one of the previous lectures. And the insight in FedWarp was that partial participation is actually the most significant source of error in Fed average. And it turns out for min-match problems, the same is true. So partial participation is actually like really hurting us, and we want to understand what can we do about it, when can we do something about it, when can we not do anything about it, and so on. So let's look at the convergence we get under full participation and under partial participation. So yeah, so this is the problem we have been working with so all along. Again, the same set of assumptions: smooth local losses, strongly concave global loss in Y. And like, just to recall a few notations, T is the number of communication rounds. Tau is the number of local steps which clients carry out during each round. P is the number of participating clients in every round. And H is the data heterogeneity across clients. So recall that we assume that the local gradient is within an H radius ball of the global gradient. Okay. In this case, let's see how the full participation and partial participation cases compare. So under full participation, meaning all n clients are participating, if we look at the expression for this gradient norm square, here phi is this function, then it looks something like this. So in the first term, we have n, tau, and t in the denominator with a square root. And in the second term, we have a t in the denominator. So if we run a large enough number of rounds, so t is the number of rounds, if t is large, in that case, this is going to be the dominant term, because here we have 1 over t, while here we have 1 over square root t, right? So for large t, the first term is going to be dominant. And this is a good thing because you see there is tau in the denominator here. So we get benefit of doing multiple local steps, right? Recall that one of the reasons for doing multiple local steps in federated learning was that it helps us save on communication. And this tau in the denominator essentially shows that we are indeed saving on communication. Okay, let's see what happens in the partial participation setting. So here, the first term is expected because now we have P clients participating in every round. So rather than an N, we get a P here. This is expected. We get a 1 over T. Again, this is expected. But we also get one additional third term. And this is coming exclusively because of partial participation. And the bad thing about this term is that we have this tau sitting in the numerator, right? So if tau is in the numerator, it means that if we do more local steps, if tau is greater than 1, then fine. The first term would improve, but the third term will become worse, right? So do we get a benefit for tau greater than 1, or do we not get a benefit for tau greater than 1? Like, this really depends. And what does it depend on? It depends on this H. So as you can see, there is heterogeneity term sitting here. So if this H is large, this third term is going to be the most significant term. If this H is small, or if it's 0, then this is insignificant. So more concretely, just to recall that in full participation, these are the computation and communication costs we get, and we do get benefit of local steps. So these results we have already seen. In case of partial participation, suppose we have homogeneous data, meaning H is zero or it is very, very small. In that case, because this term completely disappears, so we are left with these two terms, which look very similar to the full participation case. And indeed, our results are very similar. So we get, this is our computation complexity, which is we just replace N with P. And the number of communication rounds is also very similar. So in this case, indeed, there is benefit of running multiple local steps because we see this communication saving. However, if we have partial participation and we also have a lot of heterogeneous data, meaning H is larger than zero, in that case, to achieve this computation cost, we also need to do these many computations. So as you can see, we significantly increase the number of communications from 1 over epsilon square to something which depends on 1 over epsilon to the 4. And now the number of communications and the number of computations are exactly the same. So you cannot do multiple computations in each round. We are essentially forced to choose tau, which is 1 or very close to 1. So there is no benefit of running multiple local steps. It turns out this is a similar problem which arises even in minimization problems. And like this can be solved using something like Fedwall, even in the min-max setting. I think this hasn't been done so far, but intuitively it should work. So like if some of you are interested in pursuing this, I think this would be a good small work to show that even for min-max problems, something like Fedwall would work. Okay, so we started with a simple local SGADA algorithm, which assumed full participation. We generalized it to accommodate partial participation, and then we saw the consequences of that partial participation in terms of the complexity results. Let's see if we can generalize our algorithm even further. So far we have assumed that in every round, every client is carrying out the same number of local steps. Every client is carrying out tau SGDA steps. However, as you have seen earlier, in federated learning, different clients have different capabilities, they have different amount of data. Therefore, it makes sense that different clients would have different computational speeds. Like all of us have different smartphones, different laptops, different tablets. So different devices should have different computation capability. Also, different devices have different amounts of data, right? So it is really restrictive to force every client to carry out the same number of local steps. So it turns out we can indeed generalize our algorithm to allow different clients to carry out different number of local steps. So we can allow a client I to carry out whatever it decides as the optimal number of steps for it. So each client can carry out a different number of SGDS steps. One thing to be careful here is that in this case, when different clients are carrying out different number of local steps, simple averaging won't work. And you might have discussed this already in your partial participation and aggregation lecture. So an idea like FedNova, which I believe you have uh, discussed. If you haven't, yeah, let me know and I can briefly discuss it. But the idea is we need to do some clever aggregation, right? So we need to aggregate the individual iterates in a clever manner. And let's see why that is necessary. So let's first see what is the problem with simply averaging whatever the final iterate of every client. Suppose, yeah, what is the problem with simply averaging these things? What if we simply compute What is tau I? What is wrong with this? So let's understand it through the example of just two clients. Like you might have seen this already, but I want to again spell it out in the context of min-max problem because there are two variables x and y. So like just for the sake of completeness, suppose we have two clients. Client one is carrying out tau1 updates, and client two is carrying out tau2 updates. Here, tau1 is smaller than tau2, right? So starting with the same global iterate, which the server sent to the clients, they carry out multiple local steps and arrive at these two local iterates. So here, tau1 is the number of local steps at client 1, tau2 is number of local steps at client 2. Okay. Now suppose that the server simply averages these two iterates. So it takes the iterates of client 1 and client 2 and simply averages it, right? And again, tau1 is smaller than tau2. What that means is that this average, because tau2 is larger than tau1, so it is likely that the average would be more biased towards the client, which is carrying out more number of local steps, right? And you can show through examples that this simply averaging the local iterates of the two clients can result in non-convergence when different clients are carrying out different number of local steps. So this is done for minimization problems in FedNova, and this was done for min-max problems in our work, which we name FedNorm LCTA. So I'll put the reference. Actually, we referred to this paper earlier in the lecture, but we get a similar observation that if you have different number of local steps and you simply average them, then you can get you might not get convergence. So what should we do? Again, we borrow an idea which is very similar to FedNova. Okay, so what we do is, suppose these are the local iterates which the clients arrive at. Then we look at normalized updates, meaning look at the difference between these 2 points, normalize it by the number of local steps. Similarly, look at the difference between these 2 points, normalize by the number of local steps, right? So this gives us normalized updates. These are shown here in green and red. And then average these normalized updates. So we take, this is the average point of these normalized updates. This is normalized update 1, this is normalized update 2, and we take an average. But then we also scale up this normalized average. So the eventual iterate is actually a scaled up version. And what we scale up by is the number of average steps taken by both the clients. So here it would be tau1 plus tau2 by 2, right? So in some sense, what we are doing is we are multiplying this with tau1 plus tau2 by 2, and we are multiplying this with tau1 plus tau2 by 2, and adding these two together, right? Now, because as we saw that tau1 is smaller than tau2, what we are essentially doing is, because of this ratio, we are scaling down the updates from the client which did more number of local steps. And similarly, because this is greater than 1, we are scaling up the updates of the client which did fewer updates, right? So we are scaling up the contribution of client which did fewer updates, and we are scaling down the contribution of the client which did more updates. So we are sort of normalizing things across clients. Okay, and this, it turns out, averaging these normalized updates gives you good convergence. Okay, so we have done partial participation. We have allowed different clients to carry out different number of local steps. What else? Now, as I discussed earlier, because different clients have different kinds of devices, so they have different computation speeds, right? So it doesn't make sense to force all the clients to use the same optimizer, right? We are forcing everyone to use SGDA, right? This should be plus. We are forcing everyone to use SGDA, but this doesn't make sense. What if someone has more capability and can use a more advanced optimizer? It turns out we can even allow that. So we allow different clients to carry out different number of local steps, and we also allow them to carry out different kinds of local steps. So here as long as they satisfy this kind of a structure, that every local step is sort of an aggregation of local stochastic gradients you have computed in the past. So rather than just your current stochastic gradient, you can also use stochastic gradients you have used in the past. But as long as your update has this linear combination of stochastic gradients, we can allow whatever optimizer you want. So different clients can run different kinds of optimizer. And again, in that case, the aggregation will have to modify slightly. This is very similar to what was done in FedNova again. Okay. So far what we discussed was we started with one class of problems where we had, so we had these sets of assumptions and we had strong concavity in Y. And we discussed the complexity results. We discussed what kind of convergence local SGDA gets. We generalized it in several ways. Let's see if we can study another class of problems. So now these sets of assumptions stay the same, but now we remove the strong thing from strong concavity. We only allow concavity in Y. So it's a broader class of problems. And again, it turns out that for certain data imbalance problems, which are solved in this work, you can show that this smooth concave in Y, this class of problems, captures this data imbalance problem. Okay, so now things change slightly because we don't have strong concavity. So this maximization need not have a unique solution. Therefore, if we compute this function phi, it need not be smooth. Excuse me. It need not be smooth because this maximization doesn't have a unique solution. So now when we talk about stationarity, we have to look at a slightly different function. So this phi lambda, we have to look at stationarity in terms of this function phi of lambda. It turns out that phi of lambda is a smooth approximation of phi. So it closely approximates phi, but it is also smooth, while phi is not smooth. And yeah, I can point you to references if you want to understand more about this. For someone interested, this is actually a Muro envelope. So phi of lambda is Muro envelope of phi. This is a smooth approximation phi. So let's look at what kind of complexity results we can get. So what kind of computation results, what kind of communication, meaning number of rounds, what kind of computations, meaning number of stochastic gradients we can achieve. And this is the class of functions we are looking at. So perhaps the first work to solve this problem was this. It achieved certain computation and communication results, but it was very quickly improved by a subsequent work, which improved this complexity from epsilon to the 16 to epsilon to the 8. But this was in a centralized setting. This was for a single agent setting, while the first work was in a federated setting. In the subsequent work, which we did, we were able to generalize this result to the federated setting, meaning n can be larger than 1. And we also got n in the denominator, meaning there is benefit of parallelization. Everyone has to do fewer computations. We also improved the communication cost. So from epsilon to the 12, first we improved to epsilon to the 7, and then we improved to epsilon to the 4. Note that I'm not making any claims about optimality here because it's actually still an open problem. So for this smooth concave in Y class of functions, what is the optimal complexity? It's actually still open. I can say a few more words about it. So we know that this is definitely not optimal. So 1 over n to the and epsilon to the 8 is definitely not optimal. We know that it can be 1 over n times epsilon to the 6. There is an algorithm which can achieve this, but it is like it's a very complicated, convoluted algorithm. So a simple algorithm which can achieve this complexity or even improve this is so far an open question. Okay, so just to summarize, in this section, we looked at a simple federated version of the gradient descent ascent algorithm, which we discussed in the previous section. And we call this algorithm local SGDA, local stochastic gradient descent ascent. This is simple generalization of, so it generalizes local SGD. And we studied this algorithm under two sets of assumptions. In the first case, we studied smooth functions with strong concavity in Y. First, for simplicity, we assumed full participation and looked at the convergence result, the complexity results. We showed that for this class of problems, local SGD achieves optimal computation and communication cost. So optimal in epsilon, optimal in epsilon. We were able to show linear speed up in number of clients, meaning as n increases, computation per client reduces as 1 over n. So there was linear speed up. And the algorithm also worked with a constant or even a batch size of 1. This was improvement over the existing work where they were forced to use large batch sizes. Subsequently, we generalized this from full participation to partial participation. Then we also generalized it to heterogeneous computation, meaning different clients were allowed to use unequal number of local steps, different local optimizers, and so on. And then finally, very briefly, we talked about a different class of problems where we have smoothness and concavity in Y. For this class of problems, again, we were able to show linear speed up in the number of clients. So as n increases, everyone has to do fewer computations, namely these many computations. It worked with a constant batch size, but the computation cost is suboptimal. And this is so far an open problem. What is the best achievable? It has to be either this or something better than this. But even an algorithm which achieves this is open question. Okay, finally, very briefly, in the last 1 or 2 minutes, I want to, if someone is interested in some research questions in this space, I want to talk about some open questions. So I mentioned that for smooth functions with strong concavity in Y, I said that the results are optimal in epsilon, right? But whenever we have strong convexity or strong concavity, there is another factor which appears in complexity, and it's called the condition number. This is basically denoted by kappa, and it is L times mu, and it is larger than 1. So it can be very large. It can be very large for very skewed geometries, but it is always at least 1, right? Now it turns out that in the complexity for this class of problems, condition number also appears. And specifically, it appears in the following manner. So we get a kappa to the 4 for computation complexity and kappa square for communication complexity. And so far, it is not known what is the best possible dependence on condition number. The dependence on epsilon is understood, but the dependence on condition number is not understood. So this is an open question. We definitely know it is better than kappa to the 4. because for n equal to 1, people have achieved kappa square. But how do we achieve it for n greater than 1? This is again an open question. Second, as I mentioned earlier, when you have concavity in Y, then what is the optimal complexity? This is an open question. And finally, as I mentioned earlier, if you have non-convex, non-concave problems, like it's a very hard problem and a lot of work is required in this space. Also, so far I only talked about optimization guarantees. What do generalization guarantees look like for min-max problem? This is again a very open space. And finally, how do we make min-max learning more stable in general? Because of this instability, GANs have sort of fallen out of favor. But if we can make this training stable, maybe GANs would be back in fashion again. So these are some of the open questions if you are interested in. This is a recap of the lecture. And these are the two main references you can consult for this lecture. This is from ICML 2020, and this is one of my papers. Yeah, this was it. Thank you so much. I would stay if there are any questions. I would stay on for a few more minutes. Thanks, Frank. Thanks, Subin. Thanks, Yuntao.